All right, then. I think we could start. It's 5 minutes after 8 or 7 if you are in the Central European zone or whatever. So yeah, hi everyone. Thank you for coming and welcome to our events, monthly events where we talk about mostly software engineering research and mostly concerning machine learning, but not only restricted to that. So today we have Mikhail, who's a researcher at our lab at JetBrains Research. Yeah, he's going to talk about our recent work and a paper that's being published right now and then accepted, almost accepted to the journal. So yeah, I think we're going to target maybe about 45 minutes of the talk and some discussion afterwards. So about an hour and a half tops. So yeah, if you have any questions, feel free to ask them just straight ahead or write them in the chat. I'll be monitoring the chat and read them out loud if they appear. But yeah, if it's convenient to you, just feel free to turn your mic on and ask questions. Okay, Hail, mic is yours. Please go ahead.
Thank you. So yeah, indeed, please ask questions as soon as you have them. Just maybe wait me to finish the sentence, and please allow for my internet lagging because we have a storm in Cyprus right now, and somehow the storms interfere with the internet. So yeah, very happy to talk here. And today I'll talk about metrics for code generation. I will talk about our recent work with Yegor Bogomolov, Yaroslav Sokolov, and Timofey. And I will also talk a little bit on what can we do further. And yeah. Sorry. So I'll talk first of all about the code generation. Then I'll talk somewhat extensively about the metrics for the code generation. I will cover the study setup, telling how do we base on the shoulders of the giants, if I may say so. I'll describe our research questions and analysis methods, and I'll finish as usual with the results, takeaways, and ideas for further research. Right. So, okay. So the code generation problem is kind of obvious to both. You want code to be written from natural language description. And by now, we already have kind of decent models like Codex, which is, as far as I understand, embedded in Copilot, which is capable to do something nice. So the simplest case I wrote here on the slide is this example. And if we can get this properly working, we can make programming easier for the newcomers. We may even be able to remove programmers out of the loop for some very simple tasks, like, I don't know, creating a landing page for a website or stuff like that, and reduce cost of writing new programs in general. So that would reduce costs for software companies. Allow programmers spend more time on some harder tasks, and would be super nice. But obviously, it's not that easy. And yeah, and as such, we need to somehow create the models and to generate the code. And when we create a new model, we need to assess its quality somehow. So, well, the obvious choice is to do some human labeling, like to ask human to evaluate every piece of generated code and say how good is it, but that's too expensive. So there are some different metrics that we consider in this work that were all used up to some extent for assessing code generation models, and I just list them here. I'll talk about them somewhat later, but please note that there are many different metrics, and like there was even shift in popularity. So like it is true we have many different options, but somehow none of these options have ever been properly evaluated. And I'll explain later when explaining our study step what do I mean by properly evaluated. Yep. So first I'll start with the study setup, because I believe that's technically what we need to cover the first, just to explain our limitations. So the biggest problem here is that different code generation can work on a different scale, at least in theory. Maybe we are able to generate a whole long program. Maybe we are able, like Copilot, maybe we're able to generate like a one-liner, like some simpler models. But the problem is we need, the problem is we may need to assess these different programs in a different way. Like for a very short program, it probably doesn't make too much sense to assess it from, like, to try to build an abstract syntax tree, to try to build some dependency graph, stuff like that. Well, for very long problems, it is true that maybe code structure is more important. So naturally, it would be interesting to try different options. But the problem is, if you want to replicate some other people results, if you want to run some models, you're also limited by the hardware you have, and it's not technically easy to make a to run a copy of Codex on your computer, even if you get hands on Codex, because it's just too big. And that's what limited us in our choice of datasets. And from very beginning, we decided to consider Python datasets, because there is a huge abundance of Python datasets, and because there is some variety in them. And out of, I think, 5 or 6 datasets we considered, we only found 2 which were reasonable. One is CoNaLa, which is basically a dataset of one-liners in Python, with the natural language intents being Stack Overflow questions. And it is very reasonably curated dataset with some different problems, some on Pandas, some on Python for web, some on basic Python, and stuff like that. But it is one-liners, so that is a limitation. And another dataset we consider is HearthStone dataset, which is generating very rigid classes with a very rigid class structure that would satisfy certain API from a certain realization of a HearthStone computer game for the bots. So the pro for this dataset is that these classes are relatively long. They're not one-liners, so like 10, 15 lines, but the structure is extremely rigid. Like, I guess 70% of the code is virtually unchanged from class to class. But the problem is we can't really take long problems, certainly at the beginning of our study, when no strong models like Codex were available. But even later, it was not easy to get many different outputs from many different models to generate long pieces of code that would be also semantically and structurally very different. So that motivated our choice for datasets, and also created some limitations for our studies. But well, I guess that's the best we could do at that moment. And I'll move on to the research questions. So basically, there is we considered several research questions. So first research question is very much hands-on. Like, we have some models that we consider, and people claim that one model is better than the other. Is it even true? So people report something in literature. They report that old model had, say, BLEU score 30, and new model has BLEU score 30.5. Is it even true that the new model is really significantly better? Second thing we checked is how significant in general should be the difference in the results of automated metrics. So here, once again, we don't do any human labeling to answer this research question. We're just trying to answer the question. Let's say that paper A reports BLEU score, say, 30, and paper B reports BLEU score, say, 31.5 or 33 or whatever. Is this difference reasonably large to say that that the new model is better than the old one? And finally, the research question 3 touches on the subject of agreement between metrics and human assessments. So while research questions 1 and 2 are relevant for metric applicability in general, and somehow they don't even matter, for them it doesn't even matter whether we did human labeling right or stuff like that. It's more about using metrics to evaluate the generated code per se. And that's a very important point I want to make here, because basically answering this question gives a result that gives a guideline on how to use metrics, even if you create a new perfect metric that perfectly emulates human assessment. And research question 3 is about the metrics as we have them, about the applicability and relationship with the human assessment as we have them. And this is obviously also important, at least for this day, when we have the metrics we have. So, right, I'm going to move on to the metrics now, to describe the metrics we discuss in this paper. And before that, I would like to repeat what precision and recall is, because I myself always forget that. So, I mean, sorry if this is trivial for you, but I always get this mixed up. I decided the best option is to repeat that. So precision is true positives divided by true positives and false positives. So basically, we figure out how many of our predictions, how many things that we predicted were really true. And recall is true positives divided by true positives plus false negatives. So basically, it's, as it says on the picture, how many relevant items we retrieved. And this is important because metrics we are going to be discussing, they consider precision and recall, and they may have different weighting toward precision and towards recall, and there could be different motivations for that. For example, if you want to summarize a long article in a short description, you should probably aim for recall, because it's not hard to get a high precision. You just collect some words, but they don't some random words, and there is it's quite highly likely that they have appeared in this article. But you want to save the meaning, and this is because this is where the recall matters. Right. So I will go on with the metrics, and first I will describe BLEU metric, which used to be, and well, to a point still is, the go-to metric to assess code generation models. It's really unclear for me why it is the case, but still. So BLEU originated in machine translation domain, and it is precision-based. That is, in computation of BLEU, we don't consider recall at all. And thus this precision-based metric is basically geometric average for 1 gram precision, like overlap of tokens, 2 gram precision overlap of pairs of tokens, 3 grams and 4 grams. And so to avoid too short candidates, BLEU also introduces exponential penalty for the candidates that are shorter than the reference. And the obvious problem with the BLEU that we can already see here is that there is, if there is no overlap of 4 grams, that is, let's say, if every 4th token is wrong, then BLEU, according to its definition, will be 0, because it's a geometric average. So it's basically a product of 1 gram, 2 gram, 3 gram, 4 gram precision, and then to the power of 1/4. And so it means that BLEU in many setups tends to be low. And in order to avoid that, people use different smoothing options that basically make BLEU non-zero. And the problem is there are many of them, and people don't regularly report them. If you have some outputs of a model and you know what is the BLEU score of the model, it might be not easy to reproduce this BLEU score because it depends on these smoothing options. which is very much not nice, and which is very much a bad practice not to revert the smoothing options for the BLEU. Which one more thing which I dislike about BLEU is that it is a corpus level metric. That is that the average of BLEU over the samples in the dataset does not equal to the corpus level BLEU. This is not the case for the rest of the metrics we consider, and this is very much not handy because testing you have to recompute BLEU over and over and over again, and it also makes it somewhat non-intuitive. Okay. Some other natural language processing metrics that are, for example, used in machine translation are ROUGE-L, which is basically considering longest common subsequence between candidate and reference. There are various setups for ROUGE-L, but we consider the one with equal importance of precision and recall. There is METEOR, which is a very complicated metric that is described by an equation, so there is no magic, no machine learning inside, nothing like that. But it basically, but the point here is that it divides the candidate and the reference in chunks, which match between each other, and what might be necessary is to move some of these chunks, say in candidate, to match the reference, and then it does some additional weighting and stuff like that to compute the final answer. So to be true, it is I tried to compute METEOR several times by hand, and I failed because it is possible to write it as a code, but it's really hard to compute it by hand. And one more practical downside of METEOR is that its original implementation is basically a Perl script, and the other implementations, they tend to be wrong. This is one more important thing about the metrics, that you really want to use some official implementation, because, say, the obvious go-to, the NLTK package, has some problems with the metrics implementation. And for example, the METEOR implementation was terribly wrong and gave scores larger than 1 in some occasions until some recent fix. And score larger than 1 is, well, impossible, because the metrics usually score on a scale from 0 to 1. As METEOR does. And finally, there is one more metric which naively looks better for the code, ChrF. So ChrF is a metric that is weighted towards recall, and it is character-based, unlike all the other metrics which are token-based, which is like word-based for the machine translation. Here we simply consider precision and recall on 1 to 6 grams between characters. And I believe this is nice for code, because there are many different ways to tokenize the code. Say, if we have, I don't know, equal operator in Python corresponding to checking if, I don't know, x equals to 5. Does it mean that equal is 2 different tokens or 1 token? Or maybe x space equal space 5 is a single token. So there are multiple ways to argue about that, which can impact your results and which can impact your reproducibility. Any questions so far? I cannot check the chat, so please let me know you're still with me, still alive.
Yep, we're here.
Good. Right. So recently, some more metrics for assessing code generation were introduced, and the motivation for these metrics were basically that it's completely not obvious that we can use a machine translation metric for assessing code, and I'll talk a little bit more on that later. And we would like to have a metric that was created specifically for code. So we considered 2 of these metrics. One is RUBY, which was first created for code translation. And basically, RUBY is a metric that is based with logic based on like fallbacks. So RUBY tries to compare program dependency graphs between the between the two snippets. If program dependency graph cannot be built, it tries to compare ASTs. If ASTs cannot be built, it computes string similarity function. The other metric that was created specifically for code is CodeBLEU. It's basically a weighted combination of 4 submetrics. One is BLEU as usual. Another one is modified version of BLEU with additional extra weight for keywords. Third thing is match of abstract syntax trees, and fourth is data flow graph match. This metric was introduced by folks from Microsoft, and they compared it to BLEU to say that CodeBLEU is somewhat better. But I would say that the analysis was somewhat shallow, as they only compared that on one data set, and they considered certain things. They considered Pearson correlation, and it is unclear why Pearson with the human labels, why Pearson correlation is good enough to do this kind of assessment. And they did no further statistical tests. Right. Okay. Well, there are also other options. There is human labeling, as I said before, but that's too expensive. We can't afford that. And there also is an awesome option of test-based evaluation. Basically, we have tests for our snippets of code, and we check how many tests does the model pass. It is awesome in theory, but the problem is it doesn't allow to distinguish incremental improvement. So, loosely speaking, it doesn't take too much to break a program. You remove a couple of statements, and you have an enormous working program that fails all the tests. And if you look at the outputs of the current code generation models, it might be that one output passes some of the tests, but it is completely useless. And another output is perfectly passing all the tests, but is perfectly failing all the tests, but is very close to what we actually want. So until we have better code generation models, which is still unfortunately not here, until that moment we can't really afford having the test-based evaluation. Right. So why machine translation metrics can fail? Well, first, code is different from natural language. In code, we have some more knowledge, some more data, some more rigid structures, such as abstract syntax tree, data flow graph, etc., to be derived. Well, this is not the case for natural language. We can build a syntax tree for language, but say for Russian, like the order of words is very flexible. So it's really different in here. Second point here is that, say, the names of the variables, they don't really matter well from our perspective, but they matter from the perspective of the metric. We can remove the names of the variables. We can do some fix some of the naming conventions, and that's what people do when they apply machine translation metric to SS code, but still it cannot resolve all of the problems. Second reason is that none of these machine translation metrics were evaluated for the code-related tasks as of beginning at the beginning of our study, and then they were shown to fail for the documentation generation tasks. I'll talk on that somewhat later. But even if we look at the natural language processing domain, we find that the metrics are not generalizable. They are not so generalizable. For example, BLEU, the go-to metric for the code generation, is not even good for text generation. So there is, in my opinion, very little reason to believe that BLEU could be good for code generation if it fails even for the text generation. And finally, this is an open question for any metric by itself. We want the metric to map to human metric score to map to human score as close as possible. So not only, so if we label, say, on a 0 to 100 scale, not only we want human 0 to map to metric 0, we also want, say, human 50 map to metric 50, and so on and so forth. Because otherwise, when we average our metric over the data set, it may turn out that the metric does not that the metric assessment and the human assessment differ. Right. So as I mentioned, there was a study on applicability of metric for code summarization, and we derived, that was published in 2021, and we derived some of the approach from them because they really created a nice way to handle the problem, and they really created a nice way to address the problem of having many human labels for the models. So this is a paper by Roy, Arnaudova, and Fahouri, where they did the following trick. So, well, they did some, obviously they did some human labeling for the code summarization into a docstring, but then the key idea they had is creating synthetic model. So let's say you have several models. Now, what you can do is you can mix the outputs of these models to create a new kind of model, a new synthetic model, which will be created from outputs of several models that would be different from all the original models. And you can easily make a prescription by saying, replacing some of the bad predictions of some original model by the better predictions of other models to create a model that is better than the original model on a given percentage of the tasks and is identical to it on the other tasks. And this allows you to create many different synthetic models and compare them to each other, which allows you to get some statistical power for metric comparison. And then they do the pairwise comparison between these two models, between the models. And this allows them to derive some knowledge about which metrics are better or worse for code summarization. I do not repeat the results here because it would be, they have quite an extensive amount of results, but long story short, all metrics are bad, but some of them, such as METEOR and BERT score, they're better than the others. All right. So let me get back to our study pipeline. So as I said, first we need to get some code. So we generate this code with some already existing models, or we even take the code generated by the model by these models, and we compute metrics on it. Then we label this generated code. And we try to get as many labels as we can. And ideally, we would want to have 15 labels per problem, because according to the papers in machine translation, this is what we need to do snippet level analysis. But this turned out to be extremely hard. And what we did is that we collected 4 labels for one dataset and 4.5 on average for another one, which doesn't allow us to do snippet level analysis, but still allows us to do corpus level analysis. And when we get all these labels, what we do is that we aggregate them to get what we call the golden ground truth, because every human assessor may fail. Next, we create synthetic models using this golden truth as a direction for improving every original model, or maybe improving original model or making it worse. And we create many different models to compare with each other. Next, what we do is that we do so-called paired bootstrap. I'll talk on what is this somewhat in a few minutes, to find whether the difference in metric scores is significant. So please notice, no human labeling here, except for creation of synthetic models moment. We do not look at the human labels at this point. We are merely asking, okay, let's say we have these two models. One got a score of 30, another got score of 30.5. Is the one statistically, is the difference between the two statistically significant? It's basically doing lots of statistical tests to check the power of the metrics. And finally, we also do paired bootstrap to find whether the metric scores agree with humans. Okay, so any questions for the study pipeline? I guess some of what I said might not have been clear. Okay, I'm afraid. Well, I'm afraid I might have lost the audience. So please, if something was unclear, please let me know. Please let me know. All right. Moving on. All right. So what is paired bootstrap? Let's say that we have problems 1, 2, 3, 4, n, like code generation problem number 1, and so on in the dataset. So, and we have two models, A and B, which generated snippets, 1A, 2A, so on, 1B, 2B, and so on. Then we create a new kind of data set by taking this return. So I wrote the example on the slide. So basically it is a list of n generated snippets, like 7A, 3A, 7A, so on and so forth. And same for the other model, 7B, 3B, 7B, and so on. And then we compare corpus level metric scores for these two datasets. And we repeat that 1,000 times. 1,000, number of 1,000 is a little bit arbitrary, but well, it could have been 2,000 or maybe 900, but it should be quite large because of the decision we want to make further. And the decision we want to make further is as follows. We want to check in how many cases, in how many times for these choices, model A had bigger corpus level metric scores than B. If it is more than 95% of the cases, then we say that A is better than B, and this is statistically significant. If it is less than 5% of the cases, then B is better than A, statistically significant. If it is between 5% and 95%, we cannot claim that there is enough statistical significance that model A is better than model B or vice versa. Is this clear?
Yes.
Okay.
Yeah, we have a plus in the chat. Someone's listening.
Yeah. Okay. Sorry, it's really a little bit too hard without the feedback. All right. Okay. So then we go to the labeling. Now, there are many ways to label. And the way we label is important for the results we get. And basically speaking, two different approaches is either to label on a 0 to 100 scale, and then say that the scores with a difference less than some number are identical. And another approach is to label on a small scale, like ours, 0 to 4. It is debatable which scale is better. We prefer the 0 to 4 scale because it's, at least in my opinion, it is more accessible for the assessors. And here 0 corresponds to snippet that is totally relevant to the problem, maybe utter nonsense, maybe it solves completely different problem, and so on and so forth. And 4 corresponds to a perfect solution of a problem. And the figure on the right is a figure that was really painful for us to get. This is a distribution of the number of letters per snippet for CoNaLa dataset, and labeling is hard. So to label the snippets, we reached out to our colleagues, we reached out on scientific Twitter, we asked some people to help, and this was as good as we could get. I believe that in our next iteration, when we will try to label some more data, we will try to go to some labeling options such as label box, and hopefully we'll be able to get more labeling data, because asking people to label turns out to be really hard. We somewhat underestimated this task. Not much from a scientific point of view, just a word of caution for you to know. Right. Okay. So let's get to the resolution of our questions. So first question we asked was whether the existing metrics are good to compare the models we consider. And turns out that even for the original models, even for the models that were that were not synthetic, that were published and that correspond to some real-world scenarios that already happened, BLEU, RUBY, and CodeBLEU fail to agree with humans in some cases. And this is terribly bad. I mean, you look at these published papers and you find that, okay, there is some, if I apply properly, if I properly apply some of these metrics, if I do some statistical testing, it looks like these two models are equivalent, while humans believe they are not equivalent, or vice versa. So this means that the problem is real. It's not that we have cherry-picked some models, created some more synthetic models, and find some corner case. Even for the models already published, 3 of the 6 metrics don't work too well. And the worst thing about this is that BLEU and CodeBLEU are the 2 go-to metrics to assess code generation. And Ruby is the obvious next choice because it is a metric that is based on that is related to code. So this is kind of bad omen. All right. So here I give you a long and scary table, which I'll explain you in a moment. But what basically happens here? We get many synthetic models, and we compare them, and we get even more pairs of these of the models, both synthetic and non-synthetic. And we care like when the difference is statistically significant or statistically insignificant for the research question too. So we basically care what is the difference in the metric scores to claim that one metric is that one model is significantly better than the other. And it is unreasonable to go over point by point, like difference of 0.1, difference of 0.2, difference of 0.27. That's not the way to go. So here what we do is that we divide the scores into bins. So basically we look what is the delta between the 2 models for the what is the difference in the model scores, and then we separate these models into bins. Like delta from 0 to 2 means that according to say ROUGE-L, when we consider these 2 models, we have that ROUGE-L score for one is different from the ROUGE-L score from of the other by less than 2 points on a 0 to 100 scale. And then we do paired bootstrap, as I described, and we check whether this difference is indeed significant or non-significant. So I hope you're still with me here. And what's going on here is that we see that if the difference in scores is less than 2 points for the CoNaLa dataset, we cannot determine that the difference is statistically significant without statistical check. And this is incredibly important by itself, because a typical improvement reported is less than 2 points by BLEU. And it turns out that you need to do some statistical checks to prove that your improvement is indeed statistically significant. It might quite well be, because say for BLEU, I would say loosely 1/3 of the cases, the improvement was indeed significant. But still, it's far from obvious, and you need to check that. And unfortunately, people do not check that. And in many cases, it's hard to check that because you cannot easily get a replication package for some other works, which was also a nightmare for us when we tried to collect as many code generation models as possible. And this is important to keep in mind when you consider an improvement in the metric score. And also one thing that you can notice that BLEU is worse of them all, because even if the difference in BLEU scores for CoNaLa is from 2 to 5, you can't really easily claim that the difference is significant, because with probability of more than 5%, this difference is not significant. And this is very much problematic. Okay. Moving on to research question 3, I present the data once again for the CoNaLa dataset.
Mikhail, I'm sorry. I'm
Yeah.
sorry to interrupt you. Can we get back to the previous slide? Yeah. How do you comment on the disappearance and then appearance? Once again, the not significant that in METEOR when the delta
why do we have 48 non-significant for METEOR from 10 to 100, but none of that for less? That's a good one. Well, to be frank, I'm not 100% sure about that, but the problem with METEOR is that METEOR is a little bit of a black box, and it also takes into consideration the similarity between the words, like similarity between the tokens. So my guess here would be that because it is a bit of a black box, and because METEOR was developed for the text and not for the code, it might be that in some cases there is a significant difference in metric scores that is superficial, because METEOR believes that in some of the cases, like, different words are the same. And for example, this could happen when you take codex model, because it is quite verbose. So it could generate some, I don't know, some keyword which is, or maybe non-keyword, but I don't know, some programming word which is close to another programming word from the point of view of METEOR. And so it is not the same from our point of view. It is not the same from any other metric point of view. But as long as METEOR takes into account that some of the words are kind of the same from their point of view, this happens. So that is one option, but this is very much a guess in the wild.
Okay, thank you. Interesting.
Right. So yeah, moving on to comparing with people. So first thing first, we can see that all metrics are not that terribly bad. Please notice that we have difference binning here. So here, instead of usual difference according to score difference, we introduce one more bin, which is difference is not significant according to the metric, because otherwise, first it would be unwieldy to compare the results, and second, which is more important, is that, at least in my opinion, it is the difference between type 1 errors and type 2 errors is significant. Like, if the metric says that something is insignificant, if the difference is insignificant according to the metric, while in fact it is significant, I think, in my opinion, this is a lesser crime than the type 1 error, because in essence, I mean, a type 2 error won't result in publishing a paper that would falsely claim that we created a new good model. Well, type 1 error can result in that. Okay, so what we can see here. First, we can see that all metrics are bad. So for, say, delta from 2 to 5 bin, all metrics fail to agree with human is in at least 95% of the cases. A second thing we can see is that bin from 0 to 2 is superficially better than bin from 2 to 5. Why does this happen? This happens because we separate the bin from all these bins, the cases in which the difference in metric scores was insignificant, to distinguish between type 1 and type 2 errors. If we mix this thing back, then everything goes on as expected. So the 0 to 2 bin has the highest rate of mismatches, the 2 to 5 bin has lower rate of mismatches, and so on and so forth. So give or take, it is all reasonable. Third important thing here is BLEU and CodeBLEU are among the worst. So please take a look at the bin with delta in scores from 5 to 10. You can see that BLEU and CodeBLEU and also METEOR, but we didn't have many expectations about METEOR from the beginning. So these three metrics fail to agree with human judgment in at least 95% of the cases. And this is bad because, I mean, difference in scores from 5 to 10 is really huge. I mean, from superficially, this corresponds to like several years of improvement in code generation domain, many different papers by many different authors. So this is really significant, and this really highlights that BLEU and CodeBLEU are not very good metrics for code generation assessment. And while we could have very well expected that about BLEU, the result about CodeBLEU is, well, a little bit unexpected for me and quite sad. Yeah. And you also can notice that ChrF metric looks the best. It is not the best for the other dataset, which I don't showcase here because it would be twice the same number of tables with a little more information. For that one, the ROUGE-L is the best, and ChrF, I think, is second best. But still, you can see that ChrF and ROUGE-L are the best performing metrics out of those we considered. Okay, so takeaways. First, we need a new validated metric for code generation. None of the metrics we considered was good enough to work for difference in CoNaLa scores, for difference in metric scores for CoNaLa of less than 5 points. And 5 points is a very huge gap. And it is really important that we create a new metric. And unlike with the CodeBLEU case, we do a proper statistical study to prove that it indeed works, that it indeed maps well with a human judgment, and it indeed reproduces indeed matches with a human assessment for this setup like of ours, like of Roy et al., with many synthetic models with proper statistical checks and stuff like that. Because, as I mentioned, CodeBLEU people made a study which have shown that CodeBLEU is better than BLEU. It also have shown that both BLEU and CodeBLEU are not that bad, but it turns out that the result was somewhat misleading, and that is why it is so important to do this proper statistical testing. Second, if you have a code generation model right now and you want to assess it, please use ChrF. Why is that? First, it is character-based, so there are no doubts about tokenization. You just plug in your data and you get the answer, and no further doubts. Second, it is easy to reproduce, as in there is an official package that is like officially recognized by both the author of this ChrF metric and the people from the machine translation community as the package to which you refer if you want to compute ChrF. So this is incredibly important because, as I mentioned, different implementation of the metrics may yield different results because of the bugs, mistakes, different approaches, and so on. And ChrF is really easy to reproduce. And finally, and I couldn't stress that more, the best practice is to reproduce other people's results and do statistical significance tests for your model as compared to other people's model to check if the improvement is real. This is hard, and there are many cases in which replication package is not available. But all these results that I have mentioned, they really highlight that the improvement in metric scores can be misleading. And it is really important to know that you are moving in the right direction, and that the statistical significance is of your results is really there, that you can really claim an improvement. All right. Finally, I would like to talk a little bit about our further plans. So there are two things to do. First, as I said, we need a new metric. And so what we're working now together with the folks from Carnegie Mellon University is creating a metric that would utilize code embeddings to evaluate code generation quality. Something like BERT score, but for code. There are many ways to skin a cat here. You can use many different embeddings. I wouldn't say that we already converged on the approach, because in my opinion, it would be the best to mix a machine learning based metric, BERT score-like metric, together with some simple assessment for, say, short snippets of code or for some short sanity checks. And they believe that this would yield a metric that would be too prone to parameter hacking. So this is very much work in progress. but I believe this can result in a better metric, and I really hope it turns out this way. And second thing that would be really nice, on which I have thought, but on which I didn't do so far, is to create an additional statistical check to so if you having created your code generation model, would be able to compare with the works which do not provide replication package. So let me explain a little bit what I mean here. Let's say that you have a code generation model, and you know that, and you have the whole set of scores for each of the snippets, like 30, 32, 28, 27, 46, and so on and so forth. And the average is, say, 31. And you also have a result from the other paper, which only reports the average score of 30. Now, what you can do is that you can assume that the scores of each snippet, the score of each snippet in the original paper belongs to some distribution. Like maybe all of the scores for each of the snippets, they had 30 for the code generation model. Maybe half of them was 60 and half of them was 0, and so on and so forth. And then what you can do is basically you can try to compute the probability that given your scores, your model, when you can do the following. You can compute the probability that your model would beat the other model if you do the paired bootstrap, if you do some assumption about the distribution of the snippet scores according to the metric. So basically, that's some piece of math which I didn't get to, but which I would very much like to derive, and it would provide some half-good, half-baked statistical check, which would probably be not too good to report a real improvement, but which would provide a guideline. Like, I mean, it would make it easier to compare yourself with some other papers which do not provide replication package and per snippet scores and so on and so forth. And finally, as I said, it would be very nice to create a new metric. It would also be nice to create a proper human labeled data set with at least 15 labels per snippet, as this would allow us to do snippet level analysis to figure out where do metrics work good and bad. So yeah, this is it from me for today. Thank you very much for listening, and I hope I did not lose you too much on the way.
All right, thank you, Mikhail. So, any questions, comments? Yeah, Anton.
Yeah, thank you for the presentation. I wanted to ask, did you try different tokenizations, or you fixed the only one tokenizer and all the results with the fixed tokenization?
I did only one tokenizer. Well, we did only one tokenizer, which was the standard tokenizer for the models we considered. So basically, this was, I mean, it was reasonable in our opinion, and well, it would be interesting to consider the impact of tokenization. But basically, this tokenizer was reasonable, and it was used in several papers. So to be honest, we didn't think too much about trying different tokenizations.
Okay, thank you.
All right. Any more questions? Well, people are thinking. I guess I just recently found out that Mechanical Turk they improved the filtering of their assessor somehow. So now it's kind of all right to go there and hire people to label stuff related to code. So maybe we could consider using that, or I don't know, Upwork or some other platform that allows you to hire people. Or maybe we could like get some resources to actually pay for the labeling. So yeah, I'm not saying that we should do this, but I didn't consider it before, so maybe we should now. At least get the math. How much would it cost us?
Yeah, we did think about that at a certain point, and we have Vlad Tankov, who is a huge proponent of labeling something with Toloka, but I think we need what we kind of need to do is we need to do a small study on how good is the labeling. And
Yes.
I mean, not proper labeling, but I mean, to be honest, it's so much unclear for me. And the second, how good it will be. And second one, to be honest, is a little bit, is probably not too much, not too nice a thing to say, but still, reporting that we have crowdsourced the labels from some labeling platform with no information about the graders on their programming experience and so forth would be problematic.
You can get this. You can get this. You can ask them to fill some details about them. You can filter them, so it's way more advanced than it used to be when I looked at it last time. So
and
you
also
you can
also
even
give them a small
like
test.
Yeah, exactly. You can give them tests. They have reputation, and you can filter like the top X% of the people that completed some. They have, every assessor has like the completion rate and like all the kind of stuff you can use to filter. Another thing is that if you set all those filters, you might not get a lot of people, but yeah, that's a different thing. So I'm just saying that we should take another look at that. Maybe it changed. It's an old project. Okay. Anyone else?
Question.
Yeah, Danny, go ahead.
So Mikhail, thanks for the presentation. You mentioned somewhere toward the end that you expected BLEU to not perform that great, but you were surprised. I think you used the word you were disappointed that CodeBLEU, which was designed specifically for code, it also didn't perform that great. So that's also very surprising to me. Also, what were some of the other surprising results like this that you said this was very surprising? I didn't expect it to be that bad, or I didn't expect things to go that way.
So I'll talk about that. But first, I'll talk about why, in fact, I should have expected that CodeBLEU would not be so good. Let's return to the CodeBLEU definition. So here we have BLEU with additional weight for keywords.
Yeah.
And these two weights these two metrics are weighted with 0.18 weight. And we also have abstract syntax tree match and data flow graph match. And if we look closely at this, we see that AST match and data flow graph match, they're really important for big chunks of code. Because say for IST, for what I recall, BLEU does not compare the labels of the contents of the AST nodes. So as long as it is some variable here and variable there, it's good enough. It doesn't, if I recall correctly, it doesn't matter that the variables, like we use the same variable here and there. And for the shorter pieces of code, the ASTs and data flow graphs, they're kind of trivial. So there could be very many superficial overlaps and very many superficial what would be the opposite of the overlap, say misses, just let them call this way, when there is like only one change in the code and there is a significant impact towards it. Yeah, Igor, I might have made a mistake about CodeBLEU, so you want to say something about that?
Oh, no. You're exactly right about CodeBLEU. I wanted to add to the disappointments part. So out of this metric, Ruby, which is on top of this slide, it was also developed for code. And if I recall correctly, we did not find its official implementation. So we re-implemented it based on the paper, which described how they did compute the metric. But it was, while it seems from the paper initially that it is well described, there was some small part where they said that they computed edit distance between sequences, then between ASTs, then between graphs. And it was like 2 or 3 lines in the paper about it. But when you start thinking about how to do it in reality, then it turns out that for graphs, well, it is known that the edit distance cannot be computed in any reasonable way because it is like an NP-hard problem. So at this point, you just don't know how to do it. And so we decided to use some edit distance from, I don't remember, from Network X, I guess, package.
Yeah,
which seems to be like a default implementation, and it was reasonable to assume that the authors of Ruby also used this implementation, but then it makes the metric almost unusable because since computation of edit distance between graphs cannot be done in exact way in some short time, then you have to put some thresholds on timeouts on the computation, and it takes very long time for even one metric computation. So it takes like seconds to evaluate only one snippet. And if you want to do it on the scale of hundreds of thousands of snippets, then metric computation will be actually longer than generation, and it was quite disappointing, and I still don't know what to do with it, because based on the paper I did not figure out like any other way except for actually going for some graph edit distance, and well, it cannot be done in short time in any way. So I believe that our implementation of Ruby matches what they've done in the paper, but it was quite poor from the metric design perspective, I would say.
And one more comment here is that, I mean, I wouldn't say our implementation of Ruby is in any kind bad. It's reasonable. But the problem here is that if you use edit distance from network X and you put a timeout too short, you just get the wrong result and you don't understand why everything is going wrong. So we played, like I played a lot with these timeouts to make a metric run in a reasonable time. And the problem here is that, I mean, at least for our case, our Ruby metrics works fine and does not, and we don't have issues related to timeout. Like if you force network X edit distance to give you a result too soon, and just give you some kind of wrong result, and I guess due to the algorithm, due to its structure, you can't even understand that the result is so badly wrong. But if you look with your eyes, you understand that it is so badly wrong. So this is a problem here, that basically if you try to use Ruby on some previously unknown dataset, you either need to put very high timeout to be safe, and this will take lots of time to evaluate, like at least 1 second per snippet, but I would put even more if you have longer snippets. Or you cannot really be sure that, well, that your metric is actually computing what is training to be computing.
I'm just wondering if we approach the authors of the paper and ask them, hey, you know, we were surprised with that we had to put this very long timeouts, and
if I remember correctly, it was quite a long time ago, but if I remember correctly, we firstly asked them for the implementation, but we did not get the response in quite long time. So it was like a couple of months maybe. So yeah, we did not get the response. Well,
And to be
CodeBLEU
frank,
with the long timeouts, I guess, right?
yeah.
Similar with their metric, also the authors didn't reply on time.
Yeah.
And
Yeah.
to be frank, I wouldn't say Ruby is that good a metric to care this much about it. Like if you open total data on total mismatch for research questions 3, we have that Ruby has the highest total mismatch. I mean, it does work okay-ish on 5 to 10 bin, 5 to 10 different scores bin, but still it's 4.7. It's like almost on the edge. And I'm not 100% sure that if you would have some different models, it would still be 4.7. So, I mean, all in all, Ruby doesn't really work too good as a metric. And I mean, it's practically not so useful. So, you know.
But
right.
On a positive note, the takeaway from it is, which is kind of obvious, but when you want to develop a new metric, the good and easy to use implementation of it is even more important if you actually want someone to use it than like good metric design or something else. Because everyone, like a lot of studies use, for example, implementations of the default metrics like BLEU from NLTK, and it takes, I don't know, like about 5 minutes of playing with some artificial examples to break these implementations and make them output something more than 1 or less than 0, which is by metric design should be impossible. So, well, some of them were fixed at some point, but there are like numerous issues in NLTK GitHub related to them. So yeah, having a good implementation is crucial. And well, I hope that at some point we will suggest some like other metric, and we will keep this idea in mind and take more time to revise everything, test, and actually make it easy to use for others.
Yeah, Igor, that statement gets me back to the early 90s with when object-oriented programming was the cool thing, and there were a plethora of papers on metrics that were designed specifically for object-oriented analysis and design, and they were showing, oh, this is bad design or this is good design, and most of them did not survive the test of time. Like there are some, like in Chidamber paper, that's a famous classic, and some of those survived and are used in tools even nowadays in code analysis metrics, but most of them did not survive. So I wonder if there is a parallel between this is probably natural for the beginning of a field when something emerges for people to come up with lots of metrics, and most of them are not going to survive the test of time. And there is a few of them, and I suspect, based on what you said, that the ones that survived, it's because they were also decently designed, and also people made available the tools, and it was easy for others to either take the implementation or it was straightforward from the description from the definition. It was straightforward for people to compute. So I suspect that had to do something with why some metrics survives and why the majority of the metrics proposed for object-oriented analysis and design never survived. People wrote papers, but nobody cared about using them in practice.
I do agree with you in general, but I believe that for the machine translation, there is, and probably for the code generation in the future as well, there is an interesting difference. That is that actually, like, I think that using metrics for machine translation is like 20 years old, but still there is a metric competition every now and then. Obviously, with the new machine learning based metrics where you can improve your code embeddings and so on and so forth, it makes sense to improve your metric every now and then. This is very and have a new competition. This sounds very reasonable, but still somehow these results, say the results that BLEU is not so good for text generation. I think this paper was written maybe 10 or 12 years after BLEU was suggested. The results that the different implementations of BLEU give different results only appeared in 2017, as there were numerous implementations. And the problem is that even this statement that you use the exact correct implementation of BLEU is not so obvious for the practitioners. Like, I mean, I saw just so many papers which use some like an LTK implementation of BLEU just because this is the most accessible. And if you Google BLEU, the first one of the very first thing you find is an LTK BLEU. But it is not proven to be always right. And I think that it's even that an LTK BLEU does not match the proper official BLEU implementation. And this is really problematic. So I guess it's maybe because the community is wider, or maybe because there is no some kind of pressure. It's not like people, I mean, it's not that it is easy to understand whether the people use right or wrong implementation. That is why the people don't really report and use some packages which they should not be using.
I don't want to monopolize the discussion, but I'm just wondering something else about what you revealed by CodeBLEU. Like, so the testing data that we use is this one-liner Python code snippets. And then you said that CodeBLEU, because of that, and it's relying on AST analysis and also data flow. There's not much data flow in a one-liner. It's usually, you know, when you want the power of data flow, it's when you have several lines. So I'm wondering if the authors of CodeBLEU never designed it as a metric for short snippets of code. Maybe they design it for more reach, for structural, for snippets of code that span several lines, and where you can look and create some interesting data flow graphs, or where just using the AST set, matching the set of the AST nodes, if the snippet of code is longer, I'm taking it back. If the snippet of code is longer, then of course you'll have, you know, if and for statements, and so, you know, it will be a lot easier actually to match even wrong. So the CodeBLEU authors, did they ever say that it was designed for, it performs better for longer snippets, or was they never describe whether it's designed for longer or for shorter code snippets?
I don't think I saw the statement in the paper. To be honest, I need to revise it. But thing is, I mean, even if they do state something like that, it is unclear from its current pattern of usage. So say in the CodeBLEU datasets, they use CodeBLEU as one of the metrics. And the problem is CodeBLEU code generation dataset is effectively one-liners in Java, not in Python. But I still believe this is still the same.
Mm-hmm.
So yeah. All right.
I'm wondering if you reach out to, like, this would be interesting to reach out to the authors of CodeBLEU and tell them this is the result, and this is, like, we were hoping that you will perform better on these code snippets and it didn't do so well, and see what they think.
I mean, I don't know how to do that without making a personal attack, to be honest. I mean, it is true it would be interesting, but well, I mean, and when we published our paper on arXiv, it did make some splashes, but I really don't know how to reach out. I guess that's why, because I have very little experience in doing stuff like that. I mean,
I'll be happy to help you with that. So let's have a private conversation. It's not that I'm an expert, but I've done it a few times, and I've seen also how it's done badly. You know, I've been on the receiving end of how other people publish some other follow-up work after we did, and how they reached out in a bad way. So I think I've been
sure, that sounds good.
both sides of the coin. So yeah, let's talk about privately how to do that.
Let's have a private conversation. But one thing I would like to mention is that probably we need to do after the paper is published in a journal, or at least accepted, because by that point we kind of have a stamp of quality on it, and we can. It's not just an archive preprint, and like people from CodeBLEU, they know that we are not just some bunch of random folks, at least in my opinion.
Yep.
All right.
Shall I ask a question?
Yeah, sure.
Hi, this is Malinda, and I'm from University of Colorado. So, so my question is about the explainability of these metrics. So, do you think that existing metrics are explainable for the humans, and if then, what is the best explainable metric? Or if they are not explainable, do you believe that explainability is an important index when evaluating matrices?
Okay, thank you. So this is a good one. Oops, sorry. You still can see the slides, can you? Yeah, all right. I would say that out of the six metrics, ROUGE-L and ChrF, the easiest to be explained. BLEU, well, Ruby would be the next, in my opinion. CodeBLEU and BLEU would be, in my perspective, on the verge of being understandable, but still understandable. And METEOR, at least for me, is too hard to comprehend. Does it matter? I would probably say no rather than yes for the following reason. Because at least for the subjects where we have some real improvements with the metrics like machine translation, turns out that the definitely unexplainable metrics like bird score or EC, they perform so much better than the automated metrics which could be explained. So basically, well, okay, there is obviously an easily explainable part in bird score for how does it use this embeddings data to compute the final score. But the whole embeddings are obviously impossible to explain. And I'd say here, what we care more about is the metric quality. And I would say that given the current metrics, it's probably impossible to create an explainable metric that would perform okay. I mean, it would be easy to understand. It would be easy to explain why did it fail here and didn't fail there. The problem is it would not align with human judgment just way too often. I mean, just why I'm so quite confident in that, because there were some smart people trying to create all these metrics, and I mean, one of the reason of my disappointment in CodeBLEU is that it was really a nice design in my opinion, and they really did try to tune hyperparameters, these weights between different submetrics, but it still doesn't really work, and that's why I believe it's. I mean, if you create an automated metric too complicated, you can technically explain it, but you can actually explain how did your parameter hacking lead you to a nice result. And apparently, if you don't have enough parameters, your metric won't be good enough. At least I can see such a design.
Okay, yeah, sounds good. Thank you.
Thank you for the question.
Timofey, I don't know if it's I should have probably asked you before. Is it okay if we do a shameless plug for the seminar in a month from now? So myself and Malinda,
sure. Go ahead.
We're going to have we'll do the next seminar, the next presentation in this meetup, and we will talk about our approach to mine frequent changes from Python machine learning code bases and transplant those best practices and those code changes in other new code sites and new code locations. And we present this work and the results, empirical results, and also how we send these patches to famous open source machine learning projects such as TensorFlow and from the Amazon Web Services, some of their famous ones, and what was the reaction of people. So that's what we are going. It will be a talk that is more SC for ML. So I know this was more like ML for SC. This one will be like SC for ML, but I'm inviting everyone. We are excited to be talking about this and see what people think about that.
Yeah, that should be very interesting.
It's really wonderful. I'm really interested.
Yeah. Yes, if anyone is interested in like presenting their work, for example, feel free to reach out to us, and yeah, we'll figure it out. Okay, then. So I guess let's wrap it up. Thank you, everyone, for joining today. And yeah, see you next time.
Yeah, thank you for coming. It was a pleasure to have you. Hope it was not too bad. Thank you and goodbye.
Bye-bye.
Thank you very much.
Thank you.
Bye-bye.
Thank you. Bye.